Hello everyone. Alright, so let's look at another example. I would like to demonstrate to you an example of combination of current. For this case, we are given multiple types of current, and you can refer to this test number 3, 1819 semester 2, and this question actually prepared for part-time students. So if you can read from the questions, actually we are given 3 types of current, or you can say 2. The first one is our surface current density, having a Js as shown here, and this Js going along a positive z-axis with 3 the magnitude. Then we have another 2 line current. The first one, let's say here, your second line current, which starting flow at this point to the positive z at very far positions, let's say at infinity, positive. And also we have another one current, line current as well, that coming from the very far positive y, you can see, to the point, right? So we can simply say that the all current actually will contribute their own H field to where? To this our point of interest. So we are given the point of interest located at 009. So in this case we just denote as H, and we are given as well the radius of the surface current density for the structure of nickel of A. So we define it as A, and the A given as 5 meter, and also this structure of nickel having height of 5, available as L as shown here. So this surface current of actually starting from Z to 0 until Z to L, right? So we can write down the equation. The H actually, the H total that actually appear at this point of interest actually due to the H number 1 coming from the surface current structure, and then plus H number 2 coming from the second line current, and then plus H number 3 due to the third line current over here. So we need to find one by one. So let's focus the first type of current, which is our surface current structure over here. So from Biot-Savart law, we can have the dH becoming Js over ds cross unit vector of r over 4 pi r cube r squared, or this one equal to Js ds times cross vector of r 4 pi r cube. So guys, this is our surface current density. So we have to put this current element of surface current Js ds, and we know that the current now actually flowing on the side of the cylinder surface, isn't it? So the SE guys can be replaced to this value becoming r dv dz. Okay, and this case our r is remain constant at where? At A. So you can simply change the r become A. Alright, so as normal practice, so we need to take a current element on the surface current structure. So let's say this is my current element at these positions, and this is my current element, which is our Js ds, and then ds here we can replace as Js A dv dz. So at this current element we have this term. So this positions of current element is located at Z and having a radius of A. So that's why we can replace by A dv dz. If you put here, it become your z prime, so you should convert here, become z prime. So depend on your notation or labeling. Okay, so now I want to change my mode, become z. So now here become dz only. Alright, if you want to make it z prime, also here becomes z prime, because this ds is referred to the sample or current element. So let's look. And also second one, how do I find the R vector? The R vector, guys, actually is a vector that pointing from our current element to the point of interest. So let's join them. We can see. So that's going to be our R vector. Okay, the vector that actually joining the sample or current element to the point of interest. So from that diagram, we know that the R vector can be expressed in this form, coming in negative AR, because the vector is readily inward from this sample to this point. So negative AR and plus this vector up here, since going up, so you just take the distance, which is hash minus z. So here hash minus z in z directions. So that's our R vector, that joining from our current element to the point of interest. So let's substitute all this value, the R here to be here, the GS and so on to be here. So what's going to happen? You can see from here, GS also given as 3z, right? So make it here 3z component, and then the ds, so become a dv dz as shown here, and then cross with the R vector, negative a R component, hash minus z component, and then divide the whole term here by 4 pi a squared plus hash minus z squared 3/2. Okay, so that's the substitution for the R vector as well as the GS and the DS. Okay, let's do cross product between, we can see from this Z component to the R as well as Z to the Z. Okay, the Z here, cross product to the R here. We are going to have a positive phi component. Agree? So that's our conversions or product of between Z and R. And also we know that the Z plus Z will have here, the answer should be 0. Therefore, we don't have this term. Alright, so let's proceed to derivations. So this take out the 3, 4, pi, a, because they are all constants, so take out from this messy equations. So since pi here, phi, so we have a negative phi, and then 3a squared over 4 pi, and do the first integrations over the d phi. Integrations d phi, right guys, d phi here guys starting from where? You see from the diagram, the d phi here is starting from here, pi over 6 or 30 degree until 5 pi, sorry I don't, you can see from here until 5 pi over 3 or 300 degree. So just put the limit of the phi here, become pi over 6 until 5 pi over 3. So the limit of the phi, and then plus, sorry, integrate again, integrate on the dz, here become a squared hash minus z squared 3/2. And we know that guys, this sample or this current element can be located at anywhere from Z to 0 until Z to L. So that's going to be the limit of the sample or current element. So here just make it 0 to L, right? Because that's your limit of the current element. Okay, let's proceed here. So if you solve this part, you're going to have this term here is a negative phi 3a squared over 4 pi, and then this one you are going to have 3 pi over 2, and then these integrations, please refer to the study book. You can see the conversion here become h minus z negative, because now we are integrating over dz, right? So z here negative, so put here negative over a squared h minus z squared 1 over 2, and again the limit actually ranging from 0 to L, so put here 0 to L. So we can see from here, we can simply delete this a squared and this a squared, and also this pi and also this pi. So let's substitute the value of L and 0 to this z, right? Because in these equations, the h, the a, those are constant, and your variable now is a z. So z here must be used to replace the L and also the 0. Okay, again, so negative phi 9 over 8, right? So I have here h a squared plus h squared 1 over 2 minus h over L, the a squared plus h over L squared 1 over 2. Okay, if you substitute the value of h here become 9, the a become 5, then you can have this answer finally for negative phi 0.28 ampere per meter. Okay, now let's proceed to the next part, which we are going to find the h equation or the h value that due to the second line current which extending from if you see just now, I show you, sorry. Now look at to this diagram. We are going to find the H field at this point due to this line current. Okay, let's draw together. Alright, so let's say this is your line, your axis Z, and this is your H, your 9, I mean your point of interest, and then let's say this is your axis of Y, right? So, and this is your current locations at this line, and this one will go up to positive Z, the very far distance, and then this is our point of 8 here. So now we are going to find the H field that due to the second line current at this particular point. So since this is a line current that's straight in form, so you can simply use our standard equations of line current given as here. The H for number 2 become phi I 4 pi r, and then sine alpha 2 plus sine alpha 1. Okay guys, so as we discussed last time, this arc is actually a distance that distance of the line that perpendicular from the line current to the point of interest. It means that this is our line that perpendicular from line current to this point of interest. Alright, so that's our R. And now how do I find the alpha 1 and alpha 2? So since we know this is current, line current, so you can denote here, since this is your current directions, see, to the positive z directions, so you can simply denote here is your A point, initial point, and the B become very far up there, so you can join them. So join the point at here to the point of interest as shown here. Alright, so this is gonna be our alpha number 1. Remember, the A belongs to alpha 1, if your B belongs to alpha 2. So now you can see that the alpha 2 actually become 90 degree. Why? Because this line is very long in extent, and whereby with the alpha 2 will approximately becomes 90 degree. So the alpha 2 for in this case become 90 degree. Okay, now we are going to find the alpha 1. The alpha 1 can be obtained using theorem Pythagoras. So if let's say you have here is 8, here is 9, so you can have this length by adding these two sets of length, x squared plus 9 squared become 145 square root. Right? That's the length of this diagonal line. So you can see from here the sine alpha 1, right? The sine alpha 1 actually 8 over square root of 145. So you 8 square root over square root 1845. And here we'll have 1 because sine 90 degree equal to 1. And the R here actually, how long the R? The R actually the distance that perpendicularly from the line current to the point of interest, in this case is 8, right? So here change to 8, and also the R here given as, if you see, the current given as 2 ampere. So let's substitute all the value. You will see the phi 2, so 4 pi 8, 1 plus 8 over 145 square root. So this will give you the value of 34.764 milliampere per meter, but in phi directions. Okay, so now we are going to convert the phi here into the Cartesian component x and y. So the phi there we can simply convert to the Cartesian components by cross product between the unit vector of line current cross unit vector of radius that perpendicular from line current to the point of interest. So in this case, your AL guys, your AL actually lies along this line current, isn't it? So that's going to be your AL, and also your AR, actually the unit vector that parallel the line that perpendicularly from line current to the point of interest. So that's going to be our unit vector here. So in this case, we're gonna have here for this AL actually along the z-axis, z cross here that way. So bear in mind guys, the direction must always from a line to the point of interest, so here to here. So now since y, so it actually become negative y whereby you can have finally the answer is X component. So you can say that the H2, the H due to second current element, actually have X component 34.764 milliampere per meter. So that's the value of the H2 due to the second line current or second current element, second current. Okay, so now let's proceed to the second part or the last part. We are going to find the H field that due to the third current or second line current. If you draw the diagram, you can see from here. So let me draw again. Let me draw the same positions. Okay, that's going to be our line from very far positive Y to this point. So again, this is your directions of current. Okay guys, so if you look at carefully to this diagram, this line actually is still in straight line current, so you can simply use the standard equations of VSL that specifically derived for the straight line current. So we just need to find the value of R, alpha 1 and alpha 2. The rest are same, right? The same current flowing, which is 2 ampere. So from this diagram you can see that the value of R actually no longer 8, right? Because the R actually is measured on the line that perpendicularly from the line to the point of interest. So this is your line now, and so we can have this line that perpendicularly connecting this line current to the point of interest. So you can say that this will be your R. So you put the equation of VSL, so H number 3 of phi I 4 pi R sine alpha 2 plus sine alpha 1. So okay, we know that this R should now become 9 because is a line, is the distance of line that perpendicularly joining between the line current and also the point of interest. Okay, just now is 8 for the case from here to here. Okay, now let's find the value of sine alpha 1 or sine alpha 2. If you look at carefully this diagram, so the initial line going to be your A point, right? And your final point going to be your B point, isn't it? So we can see that the alpha A, which belongs to alpha 1, will result in 90 degree. Agree? Because the A point actually very far from the point of interest. So we can simply get the A alpha 1 value approximately becomes 90 degree. And how about the alpha 2? You can see from the diagram, the alpha 2 again always measured from the line that perpendicularly connecting between point of interest and also the line to the line that join them. So that is a directions of alpha 2. Okay, so guys, bear in mind, since the alpha 2 now actually against the standard directions, we normally have the alpha 2 in that side. So now we have this side which is against the standard direction, so we make sure we put the alpha 2 value become negative. Alright, so from this diagram we can get the alpha 2 value. Sine alpha 2 become what? A negative sine 8 over again. Okay, 8 over 145 square root, and then the sin alpha 1 now become 1 because 90 degree. Okay, let's put all the value inside. You are going to have this equation or this output of H3 becoming phi And now in this case we have the value of 5.935 milliampere per meter. So again, we can simply convert this phi component into the Cartesian S and Y component. So just change the phi component here. Again, it's a product of AL cross AR. So this case, AL actually along the negative Y, isn't it? So here make it negative Y. And again, the R here, actually the AR, actually unit vector along the line that perpendicularly joining from line current to the point of interest. So that's going to be your AR for this case, which is positive Z, and the output will become a negative X. Okay, so if you combine them between these two, you are going to have, so if you combine all this H from all the source of current, you can have the H total become H number 1 plus H number 2 plus H number 3, given as here. The first one just now we have the value of, let me see, minus 0.28, negative phi 0.28 plus X component 34.764 milliampere minus 5.935 milliampere, and you're going to have the total H field given as a phi 0.28 plus 28.829 in phi in X component milliampere per meter. Okay, so that's the output or the final answer for this question. So I hope you can try yourself, guys. So let me know if you have anything to ask me, so just drop a comment on the channel. All right, so thank you, all the best, good luck. All right.